This is section 2.1, and we're going to talk about patterns. So we're going to talk about patterns and inductive reasoning. So on our opener, for our opener we have this pattern. So what did I write for my pattern?
Triangle, square, circle, plus.
Triangle, square, circle, plus. So we have this pattern, triangle, square, circle, plus. And then we said that repeated, triangle, square, circle, plus. And then we said that repeated. And then on the opener we asked, so out here we have the circle, now we wanted the next two shapes. And we decided the next two shapes that this pattern repeated would be a plus and a triangle. Let's stop talking, guys. So those would be our next two shapes. This process of looking at something, observing something, maybe doing an experiment, observing, that process is called inductive reasoning. So when we look for a pattern, when we observe a pattern, when we do an experiment to try to find a pattern, we call that type of reasoning inductive reasoning. So that's what this section is about, is inductive reasoning. And that's what we use to figure out our opener. So inductive reasoning means we're using, it's based on observation or experiment. So we looked at that pattern, we looked at this pattern, and we tried to come up with a rule. What is our rule? Well, our rule is that we have these four shapes and they repeat one after the next. So we observed what was happening. We used inductive reasoning. That's what we call inductive reasoning. The rule that we came up with is called a conjecture. Conjecture is our guess as to what the pattern is, or our guess as to what the rule is. So I'm going to say our guess for the rule or pattern. So our conjecture is something that we think is true based on inductive reasoning. So we made a conjecture. We said our conjecture is this pattern is going to continue to repeat. So based on our inductive reasoning, we would say that the next two shapes would be a plus and a triangle. Now, do we know 100% certain that those two shapes would 100% certainly be the next two shapes? No, because this pattern could do something crazy in between here. So maybe it changed, maybe it would do this 10 times in a row, and then change to something else, and then go back and do this another 10 times in a row. So if we don't know 100% that this is true, we're not sure. But this is our conjecture. This would be our conjecture based on our reasoning, is that those be the next two patterns. We're not 100% certain. In order to be certain, we have to make a proof that shows that is the case for every time that something like that would happen. So what I want to do today is we're going to look at some different kinds of patterns, and we're going to make conjectures, try to figure out some rules based on our inductive reasoning, based on our observation. So let's make some conjectures. And the reason we're doing this today is, in math, this is a big part of what we do in math. We look for patterns. We look for a description of things. We try to figure out how things work, how they fit together. We make a guess based on what we see, and then we try to come up with a rule that will work for that thing all the time, 100% of the time. All right, so let's look at this pattern of numbers this time. So we want to try to figure out what the next two terms, that's what we call when we have a list like this, we call them the terms, what the next two terms would be. So who wants to make a conjecture? What do you think, Sam?
64 and 128.
Okay, so Sam says he thinks the conjecture is that the next two would be 64 and 128. And what was your rule that you used? What rule did you come up with? What are you doing to the numbers to get the next ones? Multiply by 2. So Sam looked at this pattern, he says, hey, take this number, multiply it by 2. Take that number, multiply by 2. Take that number. So if I multiply that by 2, I get 64. That number I get 128. So that's Sam's conjecture. Multiply by 2 is the rule. So these two would be the next two terms. Everybody agree? Everybody good with that conjecture? Okay. So our conjecture is we're saying the rule is the multiply by 2. And then these two would be the next two terms. Now, again, are we 100% certain that this is true? No. It seems like it makes sense, right? But this we could have some kind of thing that happens and then some other thing might happen. And so just based on these four, this would be a good conjecture, that we multiply each term by 2. All right, let's look at another one. So we're going to look at this pattern. Let me get my square drawing tool here. That one. And I'm going to draw some shapes. And these might not, I know these might not be perfect, but I'm going to do the best I can. And then I'm going to do this to this one. And I'm going to try to get it as close as mine. All right, so here's our pattern. Pretend that everything that I've drawn here is perfect, and we want the next two shapes in this pattern. So can we come up with a rule that would describe what's happening here? It'll be hard to draw these, but to come up with a description of how the next two shapes would work. So Sam has an idea, so hold on to that for a second, Sam. Let's see if anybody else can come up with something. So Lydia has an idea. So everybody keep thinking about it. I want you to think about it for a little bit. Try to look at what's happening here and see if we can come up with a description that we could use. So we got another person that thinks they know. Another one. A few more. Okay. All right. So Lydia, how would you describe what's going on here? What would be your rule? So we cut it into fourths. So each squares cutting into fourths? Right. So how many squares, how many squares would be on one side of the next shape in the pattern? How many with this way and how many this way? It would be a what by what square?
It would be 8 by 8.
Sam says 8 by 8. Is that what you were thinking, Lydia? So the next square would be 8 by 8, because we're doubling the number of squares on this side, and we're doubling the number of squares on that side. Then the next one after that would be how big?
8 by 8.
So so we make one. The next one would be 8 by 8.
Oh, it's right there.
Yeah. So the next is 8 by 8, and then the next one after that would be 16 by 16. I'm not going to draw an 8 by 8 square and a 16 by 16 square, but that's a way to describe the pattern. We double the number of squares on this side and double the number of squares on that side. They'd be smaller, but there'd be 8 across this way and 8 across that way. And by doing that, we would do exactly what Lydia said. We would cut this square into 4 pieces, and cut that square into 4 pieces, and cut this square into 4 pieces, by doing that same process. So that would be our conjecture about the next two shapes in this pattern. So we good so far?
Yeah.
So we're using inductive reasoning. We're observing, and then we're making a conjecture on what the next number in the pattern would be. All right, let's look at one that's a little more complicated. So let's say we have this pattern: 1, 2, 3, 1, 2, 3, and we want the 25th term. So we want the 25th number in this pattern. How can we go about doing this? What do you think, Clay?
I do 25 divided by 3 and then the remainder is 5.
Okay, very nice, very nice. So let's hold on to that idea. What would be the brute force method of doing this? Writing it all out and counting up to 25. So you could do that. It would be much more difficult if they asked you for the 250th term. So what Leith says is, I'm going to number these terms. So I'm going to say this is 1, 2, 3, 4, 5, 6, etc. So this is their space in the list. So Leith says because these repeat every 3, we're going to divide the number by 3. So if I divide 4 by 3, what is the remainder? 1. 3 goes into 4 once with a remainder of 1. If I divide 2 by 3, or I'm sorry, I want not 2, 5. If I divide 5 by 3, what's the remainder? 2. And if I divide 6 by 3, what's the remainder? It goes in evenly, so our remainder is 0. So I can divide 25 by 3. If the remainder is 1, my number is going to be 1. If my remainder is 2, my number is going to be 2. And if my remainder is 0, the number is going to be 3. So 25 divided by 3. So 3 goes into 25 how many times? 8. With a remainder of 1. So the 25th term would be 1. Isn't that a nice little trick? That's a nice way of doing things like this. So if our pattern repeated every 4, we would divide the number by 4 and look at the remainder. 6, divide by 6 and look at the remainder. We could do that for any kind of pattern that repeats this way. All right. Next one, a little more complicated, but not too much. We're doing really well with this inductive reasoning stuff. All right. We want to try to figure out a rule for the sum of the first 40 even numbers. First off, what do we mean by sum? Add. So we're adding. So we're adding the first 40 even numbers, and we want to figure out what that would be without actually having to add up 40 numbers. So what I'm going to do, what I suggest for problems like these is I'm going to set up a table. So I'm going to make one column is how many we're adding, and I'm going to write one column for the numbers and one column for the sum. And what we're going to do is write this out and look for a pattern. So if I just start with one number, what's the first even number? 2. And if I add 2, all I'm adding is 2. So my sum is just going to be 2. 2 numbers. So I have 2 plus, we're adding even numbers. So 4. And my sum is going to be 6. 3. So 2 plus 4 plus 6. When I add those 3 together, I get 12. I'm going to do a few of these. 2 plus 4 plus 6 plus 8. And when I add that together, I'm just adding 8 to this one. So I get 20. I'll do a couple more. 5, 2 plus 4 plus 6 plus 8 plus 10. So I'm just adding 10 to that one. And then 6. 2 plus 4 plus 6 plus 8 plus 10 plus 12, and I get 42. So the pattern that we want to look for in something like this is something that relates to how many numbers we have. Because we're talking about the first 40, so I'd end up with 40 down here. So we want to come up with a rule that tells us, that has something to do with this number. Yes. So
For how many we do 1 plus 2, and then we do 3 times 3, 3 times 4, 3, 4, 5, and then 5,
very nice. So this one is 2 is 1 times 2. 6 is 2 times 3. 12 is 3 times 4. 4 is 4 times 5. And that pattern seems to match everything that we're doing here. So if we went all the way up to 40, dot, 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 so this went to 40, I'm not going to write out all 40 numbers. We want to figure out our sum, so by our rule, it would be 40 times 41. And when I multiply that out, I get 1640. So based on our pattern, this would be 1640, 40 times 41. Excellent. That was very nice. So this is the kind of thing that we do, this kind of problem that we're going to be looking at when we're using inductive reasoning. Just to practice looking at these patterns, trying to come up with some kind of pattern. So what we're doing is inductive reasoning, and we're forming a conjecture based on our reasoning. Our conjecture is this is the pattern. So this would be the sum. This would be how we would figure out that sum. And I wouldn't want to have to write out all those or plug all those into my calculator. All right, questions on what we've done here so far? So what we're doing is inductive reasoning based on observation, and we're making a conjecture based on what we see. And we've said several times that we could be wrong. There might be something else that happens in this pattern. Doesn't seem like it, but we could be wrong. So conjectures, we don't know 100% for sure that they're true. So to make sure they're true all the time, we have to prove them. So to make sure our conjectures are true, and that's what part of what we're going to do in chapter 2, is make proofs. So these things we've come up with, we don't know that they're true all the time. So what we do to make sure they're true all the time is we come up with a way of proving that our conjecture would work all the time, 100% for any kind of circumstance. All it takes to show that a conjecture is false is one case where it doesn't work. And we call that case a counterexample. So a counterexample is an example that shows that our conjecture is false. That's what we're talking. Something that shows that our conjecture is false. And we only have to find one. Because with our conjecture, we're saying, okay, this is our rule, this is true. We find one counterexample, well, then our rule doesn't work. That might be the only exception, but that shows that that rule doesn't work. So what I want to do is, for this last part, is I'll throw out some conjectures, and we want to find counterexamples. So my first conjecture. So what we want to do here is find counterexamples. My first conjecture, if an animal is green, then it's a frog. That's my conjecture. If an animal's green, it's a frog. Anybody come up with a counterexample? What do you think, Fleur? Snakes? Anything else? A fish? A lizard? What is it? Did someone say a grasshopper? Yeah? Yeah? Could I dye my cat green? So then your cat would be green?
Grinch.
The Grinch is green, right? Could the Grinch, maybe the Grinch is a frog. That's my conjecture, the Grinch is a frog. So we'd have to find a counterexample for that. Frogs don't have hair, maybe? Alright, so any of those shows that this conjecture is false. Here's my favorite conjecture in this class. If you know algebra, then you are a math teacher. So what's a counterexample to this conjecture? Student? Everyone in this class, right? At least we hope so. We're supposed to know algebra. So you guys aren't math teachers. You might be able to be, but right now you're not. So the counterexample would be anyone in this class. And our counterexample here was a snake, a lizard, crocodile, Grinch. Our counterexample here is this class. Let's look at another one. Little more to do with geometry this time. Any three segments. Form a triangle. That's my conjecture. Any three segments form a triangle. So what would be a counterexample to this conjecture? Snakes and frogs? That was easier? So Lydia says random segments. So how about these three segments? Do those three segments form a triangle? No. And Marie said something like, okay, so here are three segments that do not form a triangle. And one we'll talk about later is, I'm going to make a triangle and I'll make the sides different colors. Try to make a triangle. Out of those three segments. What's the problem with those three segments? They won't connect. These two sides aren't long enough. And we'll talk about that a little later in the year. So these are all my counterexamples to this conjecture. Last one that we're going to look at, number 4. When you multiply a number by 2, I'm going to say the answer is divisible by 4. That's my conjecture. So, we already had one. 6, 34, 10.
I think that is, if it's 1 and base 10 is a even number and it has 2 or 6, then it's definitely not divisible by 4. Or if it's the base 10 number is an odd number, then it is followed by 0 or 8, then it's definitely not divisible by 4.
Wow. I think those are rules that I didn't even know. That's impressive. So there are rules for deciding whether or not a number is divisible by 4 based on the digits in the number. So that's a nice, that's a good example. These were more what I was thinking of. So 2 times 5 is 10. 10 is not divisible by 4. 2 times 3 is 6. 6 is not divisible by 4. So any of these are a counterexample that this conjecture is false. So those would be our counterexamples. So all we have to do is find one counterexample to show that our conjecture is false. Questions on looking for patterns, using inductive reasoning, forming conjectures, and forming counterexamples? Okay. Put your homework up, and then I'm going to pass your test back, and we're going to talk about that a little bit. I hadn't written it up on the board yet. We didn't have homework yesterday. All right, there you go.